Okay, let's read this next problem statement. We have air is compressed in a car engine from 22 degrees Celsius and 95 kilopascal in a reversible and adiabatic manner. If the compression ratio, which is V1 to V2, that's specific volume 1 to specific volume 2, is 8, what is the final temperature of the air? So in this problem, set it up first thing, we have our system is air, and the device is a car engine. So a car engine, what we're really doing the compression in is a piston cylinder. So our system here is air, and it's in a piston cylinder. So we have an idle gas and closed system process. For the conditions, we notice something very unique in the problem statement here. It says that the air is compressed in a reversible and adiabatic manner. So along with the typical closed condition or constant mass, we're also told that we have a reversible and adiabatic process. So a reversible process means that there's no entropy generation. Closed system means that there's no entropy transfer with mass, and adiabatic means that there's no entropy transfer with heat. So we have no entropy generation, and we have an adiabatic process, meaning no entropy transfer with heat. Therefore, for a closed system that's reversible and adiabatic, the other way that we can look at this is we call this isentropic. Right? If we look at the second law for a closed system process, second law for a closed system process looks like delta S is equal to the, let's write it correctly, entropy generation is equal to delta S minus the entropy transfer with heat. So as I was saying, we have a reversible process, so there's no entropy generation, and we have an adiabatic process, so there's no entropy transfer with heat. So we get delta S is equal to 0, or this is an isentropic process. For the properties, at the inlet, or at the beginning state, we have a temperature of 22 Celsius and a pressure of 95 kilopascal. For air, we need to go ahead and convert into Kelvin. We'll do that in the calculator. And the only other thing we know is the ratio of V1 to V2 is 8. And again, I'm just waiting on dyno to respond. So we know that the ratio of V1 to V2 is equal to 8. This is called the compression ratio in an engine, and it's a really important design parameter. The higher the compression ratio, the higher the efficiency of the engine. Alright, for the solution, we're looking for the final temperature of the air. Alright, so let's pretend for a second that we don't recognize that this process is isentropic. How would we normally try to solve this problem? Well, what we're doing, if we're looking for temperature at a final state of 2, and we have air, we might try the idle gas law. So we could write the ideal gas law. We don't know anything at state 2. We don't know pressure. We don't know temperature. Right? We don't know really anything else at state 2. We don't know specific volume. We only know that specific volume 2 has a ratio of V1 that is given. Also, we could look at state 1. We could try, and at state 1 we could possibly solve for the specific volume. So we could solve for the specific volume at state 1 because we know T1 and P1 and R. Then we could use the ratio of specific volume to find these two. But still at state 2, if we're looking for temperature, we would need the pressure, which we don't have. Another thing we could try to do is use the fact that for an ideal gas process, the ratio of PV over T is constant. We've also looked at this on certain problems. So if I solve for V1 to V2 as a ratio, this equation says V1 to V2, which is equal to 8, is equal to here. I end up with again, not responding, I just have to wait a second. Still waiting, just hang on a second. So basically we would need to, on the left hand side, divide out P1 and T1. On the right hand side, we would leave T2 and P2 and divide out specific volume 2. So what this is going to give us is an equation V1 to V2 is equal to 8, and then that's going to be equal to something with P1, P2, T1, and T2 inside the equation. So we're looking for T2. We know T1 and P1, but we still don't know P2 in this equation, so it still has two unknowns. Alright, finally unfrozen. So here what I'm going to do on this side, as I said, I'm going to leave V1, divide out P1 and T1. On this side I'm going to leave P2 and T2, divide out V2. So what I get on the right hand side, I have the original P2 and T2, and then I divided by P1 over T1. So T1 is going to come up top, P1 is going to go down below. Alright, and then here I know this is equal to 8. I'm looking for T2. I know T1 and P1, but I still don't know P2. So I still only have one equation and two unknowns. So if we try to solve this problem with traditional method from chapter 3, using the ideal gas law, not going to be able to get the final answer, what is T2. So one of the most important things that we need to recognize in this problem is that whenever we have a reversible and adiabatic process, then that means it's isentropic. Right? This is one of those things that I circled and highlighted in the notes as well. Isentropic means reversible and adiabatic. Alright, if we have an isentropic process, so this is not going anywhere, we need to recognize that the process is isentropic. If we recognize the process is isentropic, and we also recognize that we have an ideal gas, like air, then that opens up a couple extra equations that we learned about. In the notes, we called those isentropic and idle gas equations. They looked something like this. We had one that looked like T2 to T1 for isentropic was equal to V1 to V2 to the power of K minus 1. This is the first one we looked at. So let's look at this equation, see if we can use it. We know in this case T1, and we know the ratio of V1 to V2, so possibly we could solve for T2 using this equation if we can get K. So what is K? K is the specific heat ratio, and it's something that we can look up at T1 or T2. We can also take the average value of K. Right, in this case we don't know T2, so we're not going to be able to take the average value of K and plug it in. So since we're not able to take the average value of K because we don't know T2, we can just assume K is equal to K value at T1. And we're going to start looking up the K value at T1 for air. So T1 was 22 degrees Celsius. In Kelvin, we have 273 plus 22, that's 295. So T1 is 295, and we're looking up K. We can go to the specific heat table for an idle gas, and then we have air as our substance here. So here's the column for K of air, and again it's a function of temperature. So we see at 250 K for air is 1.401. At 300 it is 1.400. So we're going to have to interpolate to get the actual value of K that we're going to be using. So K at 295 Kelvin, that's going to be an interpolation problem. We add 250. Our value is 295. Other value in the table is 300. At 250 we add 1.401. At 300 we add 1.400. So for K we're going to be interpolating. $250, 295, 300, 1.401, and 1.400. So this is the value we're actually going to be plugging in for K, 1.4001. And then K has no units because it's specific heat ratio, C sub P divided by C sub V, so the units cancel out. Alright, now we can solve for T2. We see that T2 from that equation. Again, not responding, just hang on a second. If we multiply both sides by T1, we can isolate T2, and we're going to get T2 is equal to T1 times V1 to V2 to the power of K minus 1. Alright, and then remember V1 to V2 is just 8. So for T2, we get T1, 295 times. And we have ratio of V1 to V2 is just 8 to the power of K minus 1. So T2 is going to end up as 678 Kelvin. If it asks us to convert that back into Celsius, we could subtract 273 and end up with 405 degrees Celsius. So one thing before I explain this result is I want to go back and just see how sensitive this function is to the value of k that I use. Let's just test it out and say, for instance, I was getting lazy and I didn't actually want to interpolate, and I just used k of 1.4 instead of 1.4001. Let's just see what we would get. So instead of the actual k, let's try 1.4 exactly. So that doesn't change our answer too terribly much, 677.7. So it doesn't really change it if we round it off to 678. In some instances, our value of k, right, if we had actually known what T2 was and known that T2 was almost 700, we could see that here the k is 1.36. And then our original k that we used was 1.4. So the actual value of k that we should have been using was probably somewhere like 1.38. So let's see what happens if we use 1.38. So in this case, we change it by 0.02, and we get a temperature T2 of 650 instead of 678. So this is where k can be very sensitive in this equation. Alright, on the exam, we just want to use the k value at 300 Kelvin to make it easy. On any homework, you would always just use the average k value between T1 and T2. If you don't know T2, it's okay to assume k at T1, like we did in this problem. I just want you to be aware that this equation is sensitive to what the k value is that you plug in. Alright, back to our problem. We ended up with T2 is 678. Let's go ahead and sketch it and see why the temperature was increased. So here's our TS diagram. We have air, so we'll leave it like this, and then we have a pressure P1 of 95, and a temperature T1 of 22 or 295 Kelvin, 22 Celsius or 295 Kelvin. So in this process, we have an isentropic process. We have an isentropic process. That means wherever state 1 is, state 2 is going to be either directly above or below, because isentropic should be a vertical line on the TS diagram. So how do we know whether it was above or below? All right, it says that this problem is air being compressed. So we don't know the final pressure, but we do know the final pressure is higher than 95 kilopascal. So the final pressure would be somewhere up here. P2 is bigger than some 95 kilopascal. We know that because it's being compressed, so that should raise the pressure. That means that we go vertically up to state 2, and if you look at the temperature here, 295, here our temperature is much higher. And actually this is what we calculated as 678. So in this problem, covering a couple important things, the main thing that we're really covering that's important is that an isentropic process is both reversible and adiabatic. And if we have an isentropic idle gas process, then we can introduce extra equations into the problem statement. These are the ones that I gave in the notes with isentropic idle gas.